Today we're going to be continuing our discussion of ocean currents and how they relate to short-term changes that we observe. So I thought I'd pull up our lifetime feed on Null School here, which gives us our wind and ocean current speed as well as temperature. And so most of you have probably finished this homework assignment involving this website. And when you looked at wind directions, one of the questions asks you to look at the equator. Right? So along the equator, what directions are the winds blowing? So here we can see that that is from east to west or towards the west. And these are called the trade winds. Right? So normally this is how they will look. And because of their speed, they push large volumes of warm surface water in the same direction. So here we can see is the wind layer blowing towards the west. And also if we look at the ocean currents layer, we can see that reflected here very nicely. So we have this belt of warm surface water that congregates at the equator. So the scale indicates the temperature. So blue being cold, red being warm, yellow being in the middle. So we can zoom in here and see the speed. Right, so this ocean current is moving at about 2.1 miles per hour, and it's paralleling the wind direction. So we can see that here. You have the trade winds from below the equator blowing from southeast to northwest, and you have the trade winds in the northern hemisphere blowing from northeast to southwest. So when we go back to ocean currents here, we can see that this is basically the normal conditions. Normally, Earth always has this ocean current here that moves large volumes of warm surface water from east to west. And that's part of the natural climate of our system. But every 2 to 7 years, this movement of warm surface water flips. And that has to do with the trade winds. So the trade winds will start to reduce in speed. So they'll either slow down or they'll flip directions entirely. And instead of moving the ocean currents from east to west, they'll actually start to move that warm surface water towards the east, towards South America. So El Nino is something that occurs very often. And growing up in Southern California, you've probably heard about it a couple of times because it can affect the amount of rainfall we get here in California. So let's watch an introduction video to El Nino. Okay, so if you want to watch that video again, I have the link right here. So, what is El Nino? Basically, scientists define El Nino to be a periodic warming of the Pacific Ocean. So, here in this map on top, you can see normal conditions with color indicating the temperature. So, red being warm, blue being cold. And you can see during an El Nino event, you have this pool of warm surface water that gets pushed back towards South America due to the reduction in the trade winds. So, as a definition, El Nino is an irregularly periodic warming of the central eastern Pacific Ocean. And even though this happens in just a small region of the world, it has global consequences, right? So it basically impacts the climate from wherever you are, right? It doesn't matter if you're in India or Australia, you will be impacted by El Nino, but the impact you'll feel will be different depending on where you're located and what the normal climate of that region is. So El Nino events occur on average around every 2 to 7 years. And an individual event can last anywhere from 9 months to 2 years. And one of the most important things to remember about El Nino is that it's naturally occurring, right? So this is something that has been going on for a long period of time, long before people. So that means it's external to the long-term increase in global warming from greenhouse gases and glacial cycles. And we don't exactly know what triggers it, so we can describe what occurs during an El Nino event. We know that the trade winds weaken, and when that happens, you get a change in atmospheric conditions and rainfall patterns. And temperature of the surface water only has to rise 0.5 degrees Celsius, or almost a degree Fahrenheit, for 3 consecutive months before the scientists say, okay, we can officially declare it's an El Nino event. In the bottom here, you can see you have these red bars. So each red bar indicates an El Nino event. And the width of the bar tells you how long that El Nino event was. So although we cannot predict when an El Nino event will strike, we do know that they occur very often, right? We know that it'll only be a couple of years or so, every 2 to 7 years. But each event also is unique in duration, so we don't know how long an individual event will last. But what we do know is that it's a result of a periodic warming of the Pacific Ocean. El Nino is part of a larger process in the Pacific Ocean known as the El Nino Southern Oscillation. And you can think about El Nino as being sort of like the heartbeat of the Pacific Ocean. So during El Nino events, you will have warming in areas that are normally cold, or cooling in areas that are normally warm. But El Nino is often preceded by an opposite type of effect called La Nina. And so together, El Nino and La Nina form the ENSO, the El Nino Southern Oscillation, or the heartbeat of the Pacific Ocean. So La Nina would be the opposite to El Nino in that during a La Nina event, the trade winds would strengthen instead of weaken. So we know that El Nino is irregularly periodic, which means that it occurs often, but we're not able to predict when it will occur. And we know that it's at least been occurring for the past 13,000 years. And scientists know that by studying corals, because corals actually can record the past sea surface temperatures for when they were alive. So scientists use them as sort of like paleoclimate fossils. So we know it's a natural event that is related to a type of heartbeat of the Pacific Ocean. So let's just review a little bit of the normal conditions before we jump right into what occurs during El Nino. So before spring break, we left off talking about climate. And what drives climate? The ocean, right? The interaction between Earth's oceans and Earth's atmosphere is what drives our climate. So solar radiation is what gets this going, right? We know solar radiation is concentrated over a smaller area at the equator. So it's hotter at the equator, colder at the poles. Also recall from our last lecture, the Coriolis effect, that deflection of air currents and water currents due to a spinning Earth, is clockwise in the northern hemisphere, turning things to the right. In the southern hemisphere, it turns things to the left. And so ocean currents at the equator will follow these trade winds, right? So as a result of the Coriolis effect, right, we have these global air circulation patterns that will dictate our ocean currents, right? So here's a map of the wind belts on Earth, and then overlaid here's a map of the ocean currents on Earth. So you can flip back and forth and you can see how they compare, right? They're not exactly parallel, but they are mostly parallel. So here we can see at the equator, we have the very strong northern equatorial current pushing things towards the west, and the southern equatorial current also pushing things towards the west here. So that's a little review of the area we're going to be looking at today. So in the black box here, this is where El Nino strikes. This is where it occurs. It's in the central Pacific. So normally in the central Pacific, you have a low pressure that sits over Asia and Australia, and a high pressure system that sits over South America and the west coast of North America. And if we think back to our last lecture, right, remember high pressure systems are associated with dry climate, whereas low pressure systems are associated with a wet or rainy, humid climate. Right? So that's why it's dry in California and it's humid and wet over in Sydney, Australia. So because we have a high pressure here and a low pressure there, that means that the air is going to move. Air will always move from high to low. Right? So we have the trade winds blowing from east to west over the Pacific Ocean. So this is the normal situation. And as the trade winds blow, they push all the warm surface water also towards Asia and Australia and away from South America. And so this forms the isocline, right? So that's the layer separating the warm, distinct surface water from the colder, deeper ocean water. So normally that warm surface water gets pushed away by the strong trade winds. And as that warm water gets pushed away, remember we talked about upwelling. And because we have a volume leaving, we need to replace that volume of water. So you'll have cold, deep ocean water will rise up to the surface to take its place. So on this region of the world, on the west coast of South America, we get a famous zone of upwelling, right? So you have cold, deep, oxygen-rich water being pushed up towards the surface. And so this leads to the climactic circulation that we have here. So because this warm water normally gets pushed towards Asia, you get that warm air is less dense, right? So the water warms the air becomes less dense, it rises and releases its moisture and it forms rain. So you get a rainy, humid region on that western side of the Pacific, and generally in the normal conditions on the eastern side of the Pacific, you get dry conditions, right? With a zone of upwelling here. Okay, so now let's talk about what happens during an El Nino event. During El Nino, it begins with the pressure change. So scientists don't exactly know why the pressure change happens. All they know is that it's naturally occurring and it occurs often. So this pressure change is known as the Southern Oscillation. So you will, during an El Nino event, you will get a higher pressure over Asia and a lower pressure over South America. So because of that decreased pressure differential, the trade winds will weaken or sometimes even reverse and blow from west to east. So because of that reduced wind speed, the warm surface water sloshes backwards across the Pacific closer to South America. And the thermocline deepens along South America. So this shuts off the zone of upwelling, right? And it leads to the accumulation of warm water at the surface here. So without the strong trade winds pushing that warm surface water away, it sits over the Pacific Ocean. And so where normally we get dry conditions along South America, we're going to see more humidity and rainfall. So that's why sometimes during our California winters, we'll have a winter that's occasionally really rainy, right? And there's lots of flooding. And that's an El Nino event. We're seeing an extreme amount of rainfall due to the reduction in the trade winds. So warm surface water sloshes back, the thermocline deepens. So what are the socioeconomic effects of El Nino? So remember, upwelling is really good for biological populations because it brings up all that organic material from the bottom of the ocean to areas where fish are largely inhabited. So normally the upwelling brings those nutrients, but during El Nino, because less warm water is being pushed away, there's going to be less upwelling, right? So the reduced upwelling leads to reduced food for the fish, and then in the end, that's going to lead to reduced, economic value for the fishing industry along the coast of South America. So it's not a coincidence, right, that there's a major fishing industry off the west coast of South America. It's because of this zone of upwelling. It's sort of like a hotspot for fish. So during an El Nino event, that upwelling shuts down. And so that food source leaves, the fish leave. And so it has a lot of far-reaching socioeconomic effects, right? So El Nino itself was actually named after what occurs in South America. And the height or the peak of El Nino activity was usually around Christmas time. So in South America, they named it El Nino for Christmas after the baby Jesus. But as I said in a previous slide, El Nino has far-reaching consequences for the whole world. If we change something in the Middle Pacific, that slight change will affect all these different regions. So let's watch this video here that recaps some of the physics involved with El Nino. So let's have a look at this picture here. Part of your homework assignment will be to watch a documentary on the 1997 to 98 El Nino event. This was the worst El Nino that Earth has ever seen, and it also led to one of the worst coral bleaching events. So here we can see during El Nino in Peru and Ecuador, it's going to be warmer and wetter. In China, will also be warmer and wetter than usual. But Australia will have heat waves. It'll be very dry and it'll have a lot of fires. Whereas in California, we know that we get a lot of rainfall and a lot of flooding. So because of this, it's basically a short-term event that flip-flops the normal conditions that a region normally experiences based on this reduction in the trade winds across the Pacific. And as you'll see in this documentary, it just costs billions and billions of dollars and thousands of lives during some of these really particularly strong El Nino events. So what are some of those economic impacts? So for example, wet weather in Brazil, right? That could delay the coffee harvest. That would just be awful, right? Wet weather in Chile could lead to flooding, right? And copper mines tightening supplies. Drought in Australia could devastate production of wheat and other crops, lead to fires. Right? Reduced monsoon rains in India could lead to smaller rice and sugar crops. So it affects the whole world. It is a very far-reaching effect. But we do know that it's naturally occurring. So here we can see some of the average and maximum price changes for different commodities during El Nino period since 1991. So in the pink, that's about the average change of price in commodities for an average El Nino event. And then the dark red is the maximum that it ever saw during any large El Nino event. So you can see it's pretty dramatic, the effects that it can have on a lot of commodities that are pretty important to global production here. Look at the price of coffee during the 97-98 El Nino, 107.4. And there's also some really interesting archaeological records that correlate really well with the information that we get from ancient seawater as measured from corals. And a lot of the mass sacrifices of humans in a lot of ancient cultures was actually correlated to timings of very intense El Nino events in the geologic record. So it's pretty cool when you can start to connect some of the historical records with the scientific records. And for our local corner, right, we know that California storms are a huge problem because we have a summer season where we see a lot of fires, and that's the clearing of all of that vegetation. But then when we get a lot of flooding and we get these storms associated with El Nino, it brings up all that soil and loose regolith and tree debris, and you can get debris flows and landslides that will take out houses. So it's very important that we understand El Nino and and continue to figure out what causes it, but also to make sure that coastal properties are constructed with enough distance from actively eroding cliff lines, when we know that El Nino events are only going to increase because of global warming. So, for example, it was estimated that the 1997 El Nino resulted in about 22,000 fatalities and $36 billion in economic losses worldwide, right? So at the time, normally when I give this lecture, everybody looks at that and says, wow, that's amazing. But I mean, with what's going on now, I guess it doesn't seem as catastrophic. But it's important to understand the mechanisms involved, because Earth is a very delicate system. And if we disturb individual parts of that climate system, it has global repercussions. So I thought I'd include a slide also. Remember, I talked about scientists don't know exactly why the pressure changes in the Pacific. All they know is that it occurs often and that it will lead to an El Nino event. And so there's been some scientific research published that actually looks at El Nino as a series of smaller cycles. And basically, if you combine all of these short-term climactic cycles of these resonance frequencies, that the combination would lead to the pattern that we see for El Nino events. So they were able to link the occurrence of prior El Nino events to the correlation between these individual smaller cycles. So it's an intriguing hypothesis, right? But it's, it hasn't been proven to the point that we would say it's a theory yet. And remember, a theory is the most, poorly used word in the modern vocabulary, because everyone uses the word theory when they really mean to say hypothesis. And if you're interested in El Nino, you can visit more information here. They actually have a live tracker that you can go to and see the status of current El Nino events. So to finish off this lecture, remember in the last lecture we mainly talked about surface currents, and we just finished that now talking about El Nino. These are the wind-driven currents, the ones that move primarily horizontally. But the second current that we haven't discussed yet are deep ocean currents. And remember, these are the currents that involve vertical motion, and that vertical motion is achieved and driven by the differences in density, right, caused by the differences in temperature and salinity. So not all ocean water has the same temperature, not all ocean water has the same density. Deep ocean currents lead to something called thermohaline circulation. So deep ocean currents account for 90% of all ocean water. However, they're slower moving, right? Much, much slower in velocity than surface currents. Right? Surface currents could move a specific distance in 1 hour that it might take a deep ocean current 1,000 years to move. Right? And that's because these currents don't move by the energy imparted by wind. Instead, they're moved by differences in density. So remember, back to your core concepts, colder stuff is more dense. So colder seawater will sink, warmer seawater will rise. Saltier seawater is denser because it has more of that sodium chloride in it. Less salty water will be less dense. So we can look at a cross section here of the Atlantic Ocean. So here you can see this red line here is indicating what cross section we're looking at. So here's Greenland to the north, Antarctica to the south. And you can see the warm water pools up here at the top, right? But the rest of that, right, 90%, that's concentrated down here. So you have cold water in Greenland that's cold, so it's more dense and it sinks. You have cold water in Antarctica. It's dense, so it sinks. And notice what happens when they meet each other, right? Similar to plate tectonics, one's going to go down and one's going to stay up. So the colder, denser water, so Antarctica has the colder water here. So that water will sink below the Greenland, the Greenland North Atlantic deep water layer. So because of that, you get this thermohaline circulation. And you have to really think about the ocean as not one mass. You have to think about it as being a layered entity, right, of currents moving different directions, of different temperatures, and also different salinity, right? So they have a different concentration of salt depending on where they come from. So remember this very important concept for your next test. All deep ocean currents originate at the poles. And then that's because you have the coldest water at the poles, right? So all deep ocean currents originate in high latitude surface ocean. So here you can get two things can occur. The freezing of ice leads to glaciers, right? And so where you get glaciation, you're going to have increased salinity of the ocean because the glaciers are taking in that fresh water, right? They're taking in that fresh water and freezing it, leaving behind all that salt. So the ocean water becomes more salty and more dense, so it sinks. So once that surface water sinks, it changes a little. However, on the other hand, if you have a melting of the glaciers, right, this is going to suddenly introduce all that fresh water into the salty ocean water. So because of that, you're going to reduce the salinity, right, or decrease your salinity. And so you're going to reduce your deep water currents. So one of the main issues with climate change is that we have unprecedented melting of our glacial ice caps. And how that melting is going to affect our ocean currents, we can think of similar to El Nino, right? If we change one small thing and we change one current somewhere in the world, it's going to affect the currents and therefore the climatic patterns all over the world. So I have that same picture here again, right? So here's some of the selected deep water masses. You have Antarctic bottom water, North Atlantic deep water, right? So if you're an oceanographer, one of your duties is to map the speed and velocity, salinity of these layers. You have Antarctic intermediate water, which sits here, and then you have oceanic common water. So remember, cold surface seawater sinks at polar regions. That's where it starts and then moves equatorward. So the resulting picture is this. You have something called conveyor belt circulation. So this conveyor belt is a combination of both those deep ocean currents as well as the surface currents. So the surface currents are shown here. They're in red. And the blue currents are the deep ocean currents here. So you can see cold and salty, deep current, warm, shallow current. So the warm, shallow currents are those fast-moving currents. The blue are the slow-moving currents. And so changes in this circulation, right, whether it's melting glaciers, this can cause global climate change. So, for example, warmer surface water is less dense, so it will not sink. And so less oxygen will reach the deep ocean. This can inhibit life or shut down some of the very important microbial communities at the bottom of the ocean that lead to macroscopic life being able to thrive at the bottom of the ocean. Okay, so that was the end of your lecture on El Nino. You'll have a quiz on Canvas. Good luck with that, and if you have any questions, I'm always available via email and during my office hours one-on-one. Okay, thank you.